Hi again, Year 9s, and welcome to our lesson on experimental probability. Now, this is going to be our last lesson where we learn new things for the week, and next week we move into Pythagoras. So, we'll get right into it. So, our learning intentions for today are to know how to calculate experimental probability from an experiment or survey, to understand the effect on the experimental probability if the number of trials is increased, to be able to find the expected number of occurrences of an outcome using probability. All right, so again, to know stuff, to understand things, and then do it. Okay, so our lesson has got multiple elements here. So here's an example. A tabloid newspaper reports that 10 people were interviewed in the street, 5 had a dose of the flu. At about the same time, a medical student tested 100 people and found 21 had the flu. So what is the experimental probability of having the flu according to the newspaper? So you can see that was 5 people out of 10, which is half, quite a high number. What is the experimental probability of having the flu according to the medical student's results? So that was 21 out of 100, which is a lot lower. It's not half, because half would be 50 out of 100. Now, I'm going to pause at this point and remind you that experimental probability is the probability, I'll call it experimental PR, is the PR actually found in an experiment or survey. So up to now, we've been dealing with what's called theoretical, where it could happen. We look at all possible results and say which one matches what we want. That's theoretical. Experimental actually happens. It's actually found. So this newspaper talked to people in the street. This medical student tested people. So we can see that it's actually happening. Which of the two sets of results would be more reliable? So hopefully you agree with me and say that this medical student's results would be more reliable, not because he's a medical student, but because his survey, or the testing, looked at more people, 100 versus 10. All right, so obviously, the more people you look at, the more accurate you get data. The other thing is, and we might look at this later on, is that the newspaper people, what happens if they'd actually just sat around outside the chemist and talked to 10 people coming out of the chemist? Chances are you would have spoken to quite a few people with the flu. So there's a little bit to think about with looking at survey design and so on. So last one, using the medical students' results, because they're more accurate, how many people would you expect to have the flu in a group of 1,000 and why? So this is looking at called expected value. And this is something that pops up a lot in higher levels of maths. Expected value is a fancy name for what happens if the medical student had tested 1,000 people instead of 100. So we say, well, he found 21 out of 100 people had the flu. So what if we multiply that by 1,000? So our answer would be, if we cancel out some zeros top and bottom, 21 times 10, which is 210. So he would have expected to find 210 people with the flu. So to do this expected value, we want to do the probability multiplied by the sample, it's called, sample size. All right, so in this case, it was 1,000. So probability multiplied by sample size is expected value. All right, so we've got a few things to learn about here. We've got experimental probability, we've got expected value, and the words sample size. All right, so here's a few more things to think about and learn. This table shows the results of 3 different surveys of how many people in Perth use public transport. Survey A looked at 10 people and 2 people used public transport. So there's a 2 in 10 chance of someone using public transport. Survey B looked at 20 people, so double the size, and found 5 people use public transport. And Survey C looked at 100 people and found 30. So what are the 2 missing numbers in this list here on the right? So this would be 5 out of 20, and this one would be 30 out of 100. If we can simplify those, we should. 30 out of 100 can both be divided by 10, so that would be 3 out of 10. 5 and 20 can both be divided by 5, so that'd be 1 in 4. All right. B, which survey should be used to estimate the probability that a person using public transport, and why? Which one do you think is most accurate? Is 10 people enough to talk to, or is 20, or is 100? Hopefully, you agree with me and say that 100 is the most appropriate in these three, but I don't think it's probably accurate based on the numbers of people that use public transport at all. 100 people is just not enough. The more, the better. Question 2, the experimental probability of Jess hitting a bullseye is 5 in 100. How many bullseyes would you expect Jess to get if she threw the following number of darts? So here's that word expect, the expected value. So we remember that expected value was PR times the sample size. All right, so we know that the PR is 5 in 100. She's going to throw 100 darts. So if her chances are 5 in 100 and she throws 100, her expected outcome should be 5 bullseyes. If she threw 400, that's 4 times as many. Then we would expect that to be, cross out some zeros, and 5 times 4 is 20. Or if she threw 80 darts, that's a little bit less than 100, so it becomes a little bit trickier to do. Cross cancel some zeros. 5 times 8 is 40, but 40 out of 10 can be cancelled down to 4. 40 divided by 10 is 4. So we would expect to see 4 bullseyes there, 20 bullseyes here, and 5 bullseyes here. All right, so remember, expected value is PR times the sample. So the last thing we'll look at before I give you some questions to do on your own, a box contains an unknown number of coloured balls, and a ball is drawn from the box and then replaced. So replacement. The procedure is repeated 100 times, and the colour is recorded each time. 25 red balls were recorded. Find the experimental probability, so that's just what they told us, 25 out of 100, which is the same as 1 in 4. Find the expected number of red balls if we contained 500 in total. So we could say that we've got a 1 in 4 chance multiplied by 500, which should give us 500 over 4, which should simplify down to, what do we got? 125. 125. So the expected value here would be 125 red balls. All right. So hopefully that's given you a bit more of an idea about experimental probability and expected value. So to recap, we know how to calculate the experimental probability. We understand the effect if the number of trials is increased, and we are able to find the expected number using probability. All right, so we've learned a few things today. So if you need any help, let me know. Otherwise, you can go and try those questions on your own.